Howdy, folks. How are we all doing today? So it's a wonderful little Monday morning here. All right, you guys are hopefully enjoying your day off today. Teachers, we're still working, but I like it that way, right? So last class we looked at how to deal with different derivatives of e to the x. And so we saw the most basic derivative you can have, d over d to the x. Of e to the x. And again, I told you guys my favorite derivative. I love it. I love the simplicity of a derivative being the original function. I think that is so cool. And then we took that one step further and we dealt with what if we had a function in that exponent? We were able to do a little bit more with it, right? And we said that was it's still the same thing, but we're going to multiply it by the derivative of the exponent. The reason why we didn't have the multiply by the derivative of the exponent of just regular e to the x is because the derivative of x is 1, doesn't do anything. Well, what we're going to do today is we're going to take this from actual derivatives, and we're going to go to the next step of it. What if it was an integral? Okay. So an integral, again, just undoes a derivative. So if I integrate e to the x with respect to x, it's just going to be e to the x plus c. If I integrate e to the f of x, times f prime of x dx, that would be e to the f of x plus c. So what we're going to do today is we're just going to play a little bit. It's going to be a little bit shorter day. We're just going to play with some integrals, some indefinite integrals of e to the x, and then we'll just call it a day. So to begin with, let me throw. That was like the worst line ever there, man. I tell you what. Let's try that again. All right, that's a little better. Let's put a couple of these up here and let's see if we can't play with just a couple things here. So how about we try e to the x plus 5. Now, I'll put the next two up here, but let's talk briefly about it. Whenever you see an exponential function, we always want to go ahead and just set u equal to the exponent. We just want to make sure that we have all the pieces. So u, if I end up doing a u substitution, I don't have to here. I'll show you what it would look like if I do one in a second. But if I were to do that, I would end up with du dx, which is what I have. I have all the pieces here. So I could just go ahead and say, well, the integral of this is, since I have the the derivative is part of my differential. I don't know why I put that as an integral again. Let's try that again. There we go. If we integrate that, it'd just be that natural idea. It'd still be the same function because my derivative is the differential. Now, if I were to do a u sub, and some of you guys might choose to do a u sub on even ones like this, and that's okay. You need to figure out what makes the most sense to you. If you want to do a u sub, go for it. If you don't, then don't do it. All right, nothing wrong with that. And again, let's just write that up there. U equals x plus 5. Du equals dx. And if you choose to do a u substitution, even on ones that we have everything already for us, totally get it. Some of you guys, you just feel comfortable with u substitutions because you like to see the balance of it. And if that's you, great. If you're a person that looks and says, you know what, I don't need it, I feel okay, great. Neither one is better than the other. It's just, remember on the u substitution, make sure you put your u back in. So either or, whether you do a u substitution on it or not. Sometimes you're going to have to do a u substitution. This is one you did not have to, but it just wanted to show what it would look like if you did a u substitution. So let's have you guys try a couple of these and let's see what you guys can come up with here. How about I give you e to the 4x minus 1? And let's also try, how about negative cosine squared x? E to the cotangent x. All right, why don't you guys go ahead and pause the video and see what you guys can do with that. All right, so first up, whenever we're doing a u substitution, we always, if it's an exponential, we always go ahead and make the exponent u. So that means du is 4 dx. Well, I don't have a 4 there, so I move it to the other side. 1/4 du equals dx. All right, so we're going to plug everything in here. So I get my e, I had a u. In place of dx, I had times 1/4 du. So that means that 1/4 comes to the outside there. And now I can go ahead and take the integral of that. Integral of e to the u is e to the u plus c. So 1/4 e to, let's plug our exponent back in there, 4x minus 1 plus c. That one ended up being kind of funky looking, didn't it? Now we can fix that. Maybe. There we are. All right. Now on this one, because I have something in front of my e, I would have separated it so that way the e is out in front. So e cotangent of x. I would have rewrote this before I did anything. I like to put whatever that is with my differential so I can tell a little bit better about what kind of pieces I'm missing here. So then when I make my u my exponent, u is cotangent of x. That means du is negative cosecant squared x dx. There's my differential, and lo and behold, it turned out I actually had my entire differential. So this is just a straight u sub. If you choose to do that, some of you might look at this and say, okay, I don't need to, since I have the entire differential, I'm not going to u sub. That is totally up to you. All right. It is your call on that. So e to the u plus c. And that means then that we have to plug that back in. So e, got to get my cotangent back in there. Plus c. Apparently I wanted to mix up some colors there. All righty, friends. So we're just going to play with a few of these here, just kind of see if we can't do a little bit more, and then we will work our way into definite integrals. So let's see how you guys handle these ones here. E to the square root all over root x dx. And let's try this one here. E over, or e to the 1 over x plus 2 squared x plus 2 cubed dx. All righty, friends. Let's see how you guys end up going about that, and then pause the video. When you're done, unpause it, and we'll take a look at it. All right. So I've told you guys before. Again, we have no product rule, no quotient rule, so no chain rule per se. So I'm going to take that root x and make it 1 over root x dx. So I always take it out. Again, we want that e to be by itself if possible. So I have e x to the 1/2 times 1 over, oopsie, I lied, x to the negative 1/2 dx. So if I make u my exponent, that means du is 1/2 x to the negative 1/2. So there's my x to the negative 1/2. So we're pretty close here. I just have that 1/2 I have to get rid of. So multiply both sides by 2. I get something a little bit cleaner, and I can play with that. All right, so we do a little u substitution here. We have e u times 2 du. So we bring that 2 on the outside. That's in the wrong color. Not even close to being the right color. There we are. And we're still left with e to the u du. And that's my favorite integral. So plus c. That means 2 e to the x to the 1/2. And again, I don't have to turn it back into the square root of x if I don't want to. It's completely on you guys. Just be willing to, on a multiple choice, realize sometimes they might go ahead and put it back to being a square root of x. And if that's the case, no harm, no foul. You guys can pick up on that really quickly. All right, well, let's see how you guys did on this one. Again, I'm going to separate it again. So I have e 1 over x plus 2 squared times 1 over x plus 2 cubed dx. So again, I always, if there is a denominator or anything with the e, I always kind of pull it off to the differential. And then for me, I would have rewrote it. Hopefully you guys did too. So I would have changed this from 1 over x plus 2 squared to be x plus 2 to the negative 2. And that would have made this one x plus 2 to the negative 3. Now I can do my u sub. So u would be x plus 2 to the negative 2. So du would have been negative 2 x plus 2 to to the negative 3. So there's my x plus 2 to the negative 3 part. And I just got to get rid of that negative 2. So negative 1/2 du equals x plus 2 to the negative 3rd dx. All right, so e to the u times negative 1/2 du. So we pull that negative 1/2 out. And we can do our integral. Negative 1/2 e to the u plus c. And then we can plug it all back in there. And again, they may put it back into a denominator, they may not, you never know. So just be willing to acknowledge that it could be either or. Either or would be just fine. All right, well, we played with indefinite integrals for a little bit. Let's get some definite integrals going here. And again, what we mean by a definite integral is once we get done with our indefinite, we just evaluate. And again, when we do a definite integral, we don't need to include the plus c with it. So again, this isn't one that we needed to do a u sub, but I'll show it to you just in case. So that if I make the ux minus 2, du would have been dx. So I have the full differential up there, so it's not needed. So all we're doing on this one is we are going to evaluate that indefinite integral. So e to the x minus 2, we're going to evaluate it from 2 to 5. So e to the 5 minus 2 minus e to the 2 minus 2, which would be equal to e to the 3rd minus 1. All right, so again, same idea. We're not going crazy with it here. We're just going to do some definite integrals now that also involve the letter e. All right, so here's the two you guys are going to try, and then we will call it a day. Like I said, it's going to be a short day today. We don't need to go too terribly far with everything. The derivatives of e and the integrals of e, during a normal year, we would have done in one day. But we have the time here, so it makes it a little shorter for us and just have a little bit extra time to make sure we fully understand everything. Let's make it cosine x. E to the sine x dx. All right, friends, why don't you guys go ahead and pause the video, see what you can do, and we'll come back and we'll talk about it. All right, let's see here. First of all, I would have done a u sub on this one. So y equals 3x plus 2. So du is 3 dx. So 1/3 du equals dx. So if we plug all that in there, this would have became e to the u times 1/3 du. And we've got to go back and deal with our bounds now. And remember, when we do a u substitution, you can either leave it in terms of u, if you want to put the 3x plus 2 eventually back in, or what most of us do, I think, is we just go ahead and evaluate the values of u in. So instead of using u of 1 and u of 3, we actually figure out what those are. So 3 times 1 plus 2, that'd be 5. That means this becomes 5 here. And u of 3. So we have 3 times 3 plus 2, which is 11. So that means our upper bound just became 11. So that 1/3 is still on the outside. We can go ahead and do our integral now. And if you notice, by evaluating our u's, everything is always going to just be e to the u that we're evaluating. Makes it fairly simple, fairly straightforward. So 1/3 times e to the 11 minus e to the 5. All right, and on this one, I would have started off, I would have separated it. Pi over 4, pi over 3. And I would have moved that cosine x to the very back. Now I can see my u pretty darn quickly. So u is sine of x and du is cosine x dx. Well, I can still do a u sub on this one if I wanted to, and it doesn't really matter, but I have all the pieces there, so there's really no reason to. So we can just go ahead and integrate it. So that means this, we have everything we need. So the integral of this is just e to the sine x. So we plug it all in here. And remember, even if it's on an FRQ, if we have a trig expression, we have to evaluate it. We can never leave a trig expression as a trig expression. It has to be evaluated. So we'll do that real quickly, and then we can call it a day. Sine of pi over 3, well, that'd be root 3 over 2. Minus sine of pi over 4, that would be root 2 over 2. And friends, looks like we are golden. All right, again, good luck with that. We'll talk more about it in class, so have a great rest of the day.